That helps, I suppose. Welcome to lecture. We are going to obviously continue on in chapter 14. Hopefully, get into some chapter 15 after that. Okay, so we've been talking about sort of acid and bases and acid and base, excuse me, acid and base equilibrium, especially with weak acids and weak bases. And remember that essentially they are done the exact same way as a traditional equilibrium problem. We do use an ice table to basically solve these type of problems. We The only real main difference is at the end, we're typically interested in pH. So at the end, we're interested in either the H plus concentration or the OH minus concentration to allow us to really get to that pH. In the case of a weak acid, we would use the Ka value, solve the ice table, and when we do solve for X, that would equal the H plus concentration, which means we can directly go into the pH formula. While when we do more of a weak base type problem, that obviously needs to be a Kb value that we're using. And when we do solve the ice table, the only main difference is we're going to end up with OH minus at the end. And that would obviously mean that we first need to get to the POH and then like subtract 14, and that will get you to your pH. So we could do the same stuff that we've done with equilibrium problems. You could try an assumption. A lot of cases it will work, but some cases it will not. You could also obviously solve it the quadratic way as well. But pretty much done the same way on those guys. And again, that's obviously very different than a strong acid or strong base, which because they're strong acids or strong bases, they will 100% break apart into ions, and pretty much directly from the formula without doing an ice table, obviously, you could get the H plus or OH minus concentration depending on which one that you need. Any questions on the stuff we talked about last time? Again, if you do have questions, feel free to type them in as we go along, and we'll try to obviously get those questions answered for you. Just rearranging a few things here. All right, so I think where we left off was right around here. So we've talked about weak acid problems, we talked about weak base problems, and obviously Ka and Kb. And that gives us our two sort of K values associated with our acids and our bases. So here again is some generic formulas for the first one, obviously, is a weak acid dissociating into H plus. The second one is considered a weak base there and producing OH minus. And as I talked about last time, that is your big sort of hint when you're doing future problems as well, you know, what type of K value you should be using. Again, if you see the H plus or H3O plus on the product side, you definitely should be using a Ka value in those type of problems. If you see you produce OH minus, you definitely should be using a Kb value. And that's why, as we talked about, it is sort of important to know how to sort of properly write these equations so that you can see what is actually being produced. But there is a relationship if we actually add both of these reactions together. So if we take our weak acid reaction and add it to our weak base reaction, we will actually get this overall reaction here, which might look familiar to you. And that is actually water. So again, if we take the weak acid reaction, add it to our weak base reaction, we actually get the overall relationship, which is basically the formation of water. Remember, when you take like an acid and base, right, two things you make is salt and a water. Salt being obviously an ionic compound, water coming from usually the H from the acid and the OH minus from the base. And water has its own K value associated that we talked about, which is Kw. And that's a really important relationship that you can use, which is if you take the Ka value and you times it by the Kb value, you'll get Kw. And that Kw, again, is that 1 times 10 to the minus 14 in most cases. And this is a very useful relationship, especially as we'll talk about here shortly when we get into sort of hydrolysis reactions. there will be certain problems where it is very common that they will give you the Ka value when you actually need the Kb value and vice versa. So this is a very convenient way where if you have Ka or Kb, you could solve for the other one by simply taking 1 times 10 to the minus 14 and dividing it by either the Ka value or the Kb value. So this is, again, a very important relationship, and we will definitely see it a little bit later on here in this chapter when we start talking about salts. These are polyprotic acids, and polyprotic means that it has more than one H plus that it can basically give away. And what I'm going to do actually for the time being, I'm going to come back to this. So we're going to come back to this, so don't cross it out or anything like that. We'll come back to that. We will do that problem here in just a little bit. But I actually just want to kind of go forward first and talk about a couple other things, and we'll actually finish the chapter going back and talking about that one example there that we just kind of passed. So the next sort of topic I want to sort of talk about is acid strength. And the strength of the acid does really depend on the type of acid that we're dealing with. And in the case of this type of acid that we see on the screen, these are acids that do not contain oxygen. So these are things like HF, these are things like HCl, HBr, HI. And really, when you look at an acid that does not contain oxygen, there is a couple of things you may look at to try to determine, what makes it a stronger acid versus another. And really, the basic definition of an acid is what you should look at. Really, your basic definition is the ability to produce free H plus in solution. And what that means is you have to essentially get the H plus out of there or off where it's connected now. And you may be tempted to think, when we look at something like group 7 here, in terms of electronegativity, right, it increases as we go up. And electronegativity increases as we go up, and right, electronegativity, for example, like HF, right, partially positive here, partially negative here, fluorine being the most electronegative. You would think that because of that big separation there, that would weaken that bond and allow the H plus to actually come off a lot easier. And when we look at this type of acid where we are looking at one that does not contain oxygen, it's actually not electronegativity that's the important thing to look at here. So it's really not electronegativity to look at in this type of acid. It is actually bond strength or bond enthalpy. Perhaps you remember delta H, right? Bond enthalpy, all the bonds making, all the bonds breaking, right? Products minus reactants, and you kind of get your bond enthalpy or energy. And it's the bond strength, which is sort of the overwhelming thing that you want to look at when you're comparing acids that do not contain oxygen. So when we look at bond energy, if you look in this table here, what we see is the strongest bond energy is actually between HF, which means the bond between HF is a really strong bond. And what that means is HF is actually going to be a weak acid. So you may say that's maybe opposite of sort of what it sounds like, but it does have to do with this idea here of releasing that H plus. So if this HF bond takes the most energy to break, it's going to be harder to remove that H plus, and the H plus is going to hang on there a lot longer and thus not produce free H plus and would be a weaker acid. As opposed to we get down to the bottom of the group there where we have our HI, it's much weaker. So what that means is when we look at hydroiodic acid, the bond between the hydrogen and the iodine is relatively weak, which means it doesn't take a lot of energy to break that bond apart. And if it doesn't take a lot of energy to break that bond apart, that means the H plus can come off pretty easily. And if the H plus can come off easily, that essentially means it's a stronger acid. So when we look at this type of acid, again, that does not contain oxygen, the order of strength is what we see on the bottom there. HI, which has the weakest bond energy, is the strongest acid because it's much easier for that H plus to come off, while HF would be the weakest acid in that group because it has the highest bond energy, which means it's a lot harder to remove that H plus, and thus it makes it a weaker acid. So in terms of strength of acids in group 7, as you can see, it increases as you go down group 7. As you come down group 7. Any question on that there? Okay, so let's then talk about acids that actually do contain oxygen. And when we deal with acids that contain oxygen, there is a couple of things that we look at when we're trying to determine what one would be a stronger acid. And that is either electronegativity. And just a reminder, electronegativity is the ability of an atom to bring electrons towards itself. Hopefully you remember, right, on the periodic table, that increases as you go up, right? So we'll go here, electronegativity. Increases up, right? And to the right, and decreases obviously the other way, right? So going left and down on the periodic table, electronegativity decreases, fluorine being the most electronegative element you could have. The other thing that we look at is the oxidation state of the center atom. Oxidation state is where we look at sort of the charge in quotes of the atom if all the electrons were transferred. And again, oxidation state is a little bit different than actual charge, but that's something we look at. So these type of acids are what are referred to as oxyacids because they contain oxygen. And again, depending on the type of oxyacid you're comparing, you do have to look at a couple of different things. So let's take a look at the two sort of common ways to compare different types of acids. The first two acids that we're looking at here, these are acids that have a center atom from the same group and they have the same oxidation number. So just to make sure, when you're assigning oxidation numbers, oxygen is a really good place to start. It has an oxidation number of -2. So this would be -2, that would be -2. Hydrogen is +1 in most cases. So that's -2, -2, -2 is -6 for all the oxygens and +1 there for our hydrogen. So to balance that out, the oxidation state of chlorine in this case is +5. So again, remember, oxidation state is not necessarily the charge we usually associate with things. We usually think about chlorine as being -1 when it becomes chloride. But the oxidation state, again, is sort of the charge it would have in that sort of situation that it's in. Same thing, we come over here, -2, -2, -2, and +1 for hydrogen. So again, you can see here, the oxidation state of our center atom is also +5 in this case. So here we have basically the same oxidation state on all of the center atoms. We essentially have everything on the outside exactly the same. So we obviously can't look at oxidation number to help us determine which one would be the stronger acid. So we have to look at electronegativity. And when we look at electronegativity, again, chlorine is higher up, which means it's more electronegative. So let's talk about what really will make this an acid. It's this bond right here. This is sort of the bond we have to break, right, to liberate the hydrogen there in both of them. This bond already, as you hopefully also should know, is a polar bond, right? It is partially positive on the hydrogen, partially negative on the oxygen. What that essentially means, if you want to think about it this way, is the electrons in that bond itself are heading in this direction. So what that means is, as these electrons head in this direction, because this chlorine is more electronegative, it will kind of pull the electrons a little bit more. So I'll just draw a little bigger, exaggerating, obviously. It will kind of pull those electrons a lot more in. And what that's essentially going to continue to do is weaken that OH bond to a point where the H will pop off. Now, when we look at bromine, the same thing is going to happen. These electrons are heading this way. This is less electronegative in comparison to our guy on the left. So it will just kind of pull the electrons a little less. So this bond here will still be weakened, but it'll be still stronger than the bond we see on the left. So in terms of strength, we would expect the HClO3, the chloric acid, to actually be a stronger acid than the bromic acid because of the electronegativity of our central atom. Any questions on that? So in this type of acid, which is an acid that contains oxygen, if the center atom has the same oxidation state, what we look at is the electronegativity value of those center atoms to help us determine which one is stronger. The higher the electronegativity value, the stronger the acid we would have. Now, we could also have a oxyacid that comes from the same element, for example, but has different guys attached. And obviously, if we're comparing acids where has the same central atom, we can't look at electronegativity because they're going to have the same electronegativity. So what we want to look at in this case is actually the oxidation state of the center atom. And when we look at the oxidation state in these three acids here, or four acids, again, if we start with -2 for our oxygen, +1 for our hydrogen, that gives us a -1, which means in this case, the chlorine has a +1 oxidation state. -2 here, -2 here, +1 gets us a +3 oxidation state to balance out the charge. This is just like the one we saw earlier, -2, -2, -2, +1 gets us a +5 oxidation state. And now -2, -2, -2, -2, and +1. And as you can see here, that is 2, 4, 6, 2, 4, 6, 8. And +1 is -7. So this, again, as you can see there, is +7. So what does this mean? It's really the same idea as what we were just talking about. Again, we already have this hydrogen-oxygen bond that's weakened by the polarity of it. But now when we get those larger positive oxidation numbers on that center atom, it's just going to help those electrons kind of move more and more in and weaken this bond and allow that H plus to come off a lot easier. And that means that the higher the oxidation number of that central atom in a situation like this, the stronger acid it would be. So in this case, we would have perchloric acid, chloric acid, chlorous acid, and hypochlorous acid in terms of our order there, in terms of strength. Again, following basically our oxidation number. So that's basically the second way that you can sort of look at acids and compare them is by oxidation number or electronegativity. And those are the two things you want to look at when you're dealing with an oxyacid, an acid that contains oxygen. Any questions on that there? Okay. So the next thing we're going to really talk about here are salts and reactions of salts. So hopefully as well, you remember that when you do take an acid and base, right, and you react an acid plus a base, you basically produce two things. You get water plus a salt, right? And a salt is really just an ionic compound, a positive negative guide together. And in certain cases, these salts will be neutral, which means they're not very reactive. So they won't continue on to react. And really, when we talk about it being stronger or continuing on to react in this type of reaction here, we're talking about the ability of the salt to then react with water. And that process is what is sometimes referred to as hydrolysis reactions. When a salt and a water will react. So what can happen in certain cases is we produce this salt really as a result of a reaction of an acid and base together. And the salt sometimes has the ability to further react. And what it has the ability to essentially do is affect the pH of that solution, because in certain cases, it can further react and produce more H+, which will obviously affect the pH. And in certain cases, it can further react and produce OH minus, which would obviously affect the pH as well. So there are neutral salts, and neutral salts essentially contain either group 1 or group 2 on the periodic table, except for beryllium, and the conjugate base of a strong acid like Cl minus, Br minus, NO3 minus. So if you remember earlier in this chapter, we talked about the relationship between an acid and its conjugate partner. And if you remember, if the acid is a strong acid, or if the base is a strong base, its conjugate partner will be relatively weak. And that's opposite than if we had a weak acid or a weak base, its partner on the other side will be relatively strong in terms of its conjugate partner. And basically, salts that come from really strong acids or strong bases basically will be what are referred to as neutral salts. So we would expect the pH of a solution that contains sodium chloride to be a pH of 7, which would be neutral in that case. And really, when you look at a salt in this sort of situations, sometimes it's important or good to try to think about where that salt came from. So when we look at a salt like sodium chloride, you should hopefully be able to figure out that perhaps the salt came from sodium hydroxide and hydrochloric acid, right? The sodium hydroxide probably providing our sodium ions, the chloride here providing our hydrochloric acid providing our chloride ions to produce our salt. And sodium hydroxide is a strong base, which means its partner will be relatively weak. And hydrochloric acid is also a strong acid, which means its conjugate partner there, the Cl minus, will be also really weak. So if you think about group 1 and group 2 on the periodic table, those are a lot of things that come from strong bases like sodium hydroxide, potassium hydroxide, barium hydroxide, and so forth. So if you see a salt that's basically made up of anything from group 1 and group 2, and anything where the Cl minus part comes in, that's going to be a neutral salt, and we would expect the pH to be 0. Not 0, 7 would be a better pH there. So for example, Cl minus comes from hydrochloric acid, Br minus comes from hydrobromic acid, which is also a strong acid. NO3 minus, which is nitrate, comes from nitric acid, which is obviously also a strong acid as well. Yeah, so in general, when you see something like Cl minus, Br minus, NO3 minus, for example, you want to think about acids that contain those things. And since we're talking about obviously acid-base reactions, so since a salt basically would be produced from an acid and a base reacting, we want to think about these things in terms of like acids and bases. So we know that most likely Cl minus came from pretty much the only acid that has Cl minus as a sort of conjugate partner, which would be hydrochloric acid. So that's sort of how we sort of got that from. And then usually in most cases, you could kind of think about the Na plus part is probably going to come from sodium hydroxide. Again, a lot of those strong acids and a lot of those strong bases come from group 1 and group 2. So that's why they say here, not specifically that it comes from a strong base, but again, group 1 and 2 on the periodic table, which is your alkali metals, your alkaline earth metals, those are essentially where we produce pretty much all kind of strong bases. And so essentially we can almost make the sort of jump, if you will, that the base here would probably be sodium hydroxide in that case. In theory, it could be something else with sodium, but most likely going to probably be sodium hydroxide in this case because we're really specifically talking about acids and bases sort of reacting together. Okay, so if you have a salt that comes really from anything that is a strong acid or a strong base, it's going to be really considered a neutral salt. And you really don't have to do any type of calculation or anything like that. You could just assume that it is going to be 7. Now, there's also salts that will be basic salts. And for example, if we take something like, that is like not good, so I'm just going to write it here. I don't like the way that looks. So I think that has an extra H on it, so you could get rid of it. But let's say we take something like sodium acetate here. Now, sodium acetate, when it breaks apart, will break apart into two things. It will break apart into sodium ions and acetate ions. Now, when we look at sodium ions and the acetate ions, we want to think about where, again, these guys probably came from. So if you had to make a pretty good educated guess as to how you produced your sodium acetate, it is most likely going to be a reaction of sodium hydroxide plus some acetic acid. And again, basically what's going to happen is a double displacement, right? And you're going to get your sodium acetate and your water there. I missed my arrow. I went too far, I think. Now, when we look at these guys, we can see that this salt is what we're dealing with here, and that's most likely where it was generated. And why that's important, again, is it gets you in the mindset of thinking about that relationship of if it's strong, then his partner is weak, or if it's weak, his partner is strong. So when we think about the sodium ion, we can see it comes from group 1, but really also sodium hydroxide, which means in terms of the pH, in terms of reactivity, this is going to be neutral, essentially, as we saw up here. So it's just like up here. But when we look at our acetate, it most likely came from acetic acid. And acetic acid, as you hopefully know, is a weak acid, right? And because the acetate part came from a weak acid, is going to be relatively strong. And again, not strong as like a strong anything else, but it's going to be relatively strong, which means it will react with water. So what's going to happen when you have a solution of something like sodium acetate, or you produce sodium acetate as a result of a reaction? The sodium part's not going to do anything, but now the acetate part here will then continue and actually start reacting with the water that's also produced in that reaction, right? So what's going to happen is we're going to have our acetate that was really produced from that reaction is going to react with water. Now, the important part to think about and why it's important to think about where these things come from is if this acetate came from acetic acid, which is a weak acid, that means that technically speaking, the acetate is the conjugate base, right? So technically speaking, the acetate's the conjugate base from the weak acid of acetic acid. And that's really important here because when the acetate goes to react with the water, it's going to react as a base. And the definition of a base is something that will accept an H+, which means in this case, the H+ is then going to come from the water over to our acetate. And we're going to get this reaction that will produce acetic acid. And it will produce hydroxide ions. So a couple of things that we see in this reaction that's important. First thing is we see that we produce acetic acid. And in these type of reactions, these hydrolysis reactions, you essentially will always produce where the salt came from. So acetate came from acetic acid. We just produced acetic acid on the product side. So that's something that always sort of happens. But more importantly, in terms of the pH here is we are producing, as we can see on the product side, OH minus, which means if we wanted to make an educated guess on whether this solution is acidic, basic, or neutral, because we are producing OH minus, we know right off the bat without even doing a calculation that this solution should be basic because we are producing OH minus. And that means that if we took the pH of a sodium acetate solution, we would expect to find the pH in the basic range because it's producing OH minus. We're also going to talk about how to do these calculations here in just a second, but also important is because I'm producing OH minus, the K value that I should use for my calculation should be a KB value. And why that is important is, if you remember, not too long ago, I said that there are definitely problems where they give you sort of the wrong K value. And this is these type of problems. When you deal with hydrolysis problems and you deal with salts, typically speaking in those problems, you would be given the Ka value, for example, of acetic acid in this problem. And you would not need the Ka value. You would actually need the Kb value to solve this problem. And that is where what we saw earlier comes into play, that the Kw equals Ka times the Kb. So this is a place where you can use that relationship that we saw earlier to quickly get the Kb value that you would need in this reaction. Any questions on that part? So essentially, if you have a salt that came from a strong base and a weak acid, it will actually produce a salt that will go through hydrolysis, which means one part of the salt will continue to react with water. When it reacts with water, it's going to react as a base and accept an H+. And the important part is you're going to produce hydroxide ions, and it's going to give you a basic pH. Any questions on any of that? All right, then let's talk a little bit about acid type salts or acidic type salts. Just move some things around here. All right. And again, on your handout there, you can kind of see it right here. There's an extra H there. This shouldn't be, I don't believe. Let's cross it out there. All right. Now, there are salts that are considered acidic salts, and these are salts that come from a strong acid and a weak base. And if we take something like ammonium chloride, again, if you had to kind of step back and try to figure out where those things came from, ammonium most likely came from ammonia, NH3, and HCl, this reaction, which would give you NH4Cl, basically, yeah? And what we know when we look at the parts of ammonium chloride, as we saw earlier, the Cl minus most likely came from HCl, which means it comes from a strong acid, which means in terms of pH, we're not going to worry about it because it does come from a strong acid. It's going to be neutral. But when we look at the ammonium, it actually comes from ammonia, which is a weak base. So what that means is this NH4 plus will actually continue on and react with water and go through hydrolysis. So the reaction that we would see would be the NH4 plus, I'll spit that out, right, I think, plus the water. And same sort of logic, the NH3, which is a weak base, which means technically speaking, this would be our conjugate acid. And that's important because this is going to act as an acid when it reacts with water, which means it's going to donate as H+ over. And when it does, we will get NH3 and H3O+. Just like what we saw in the previous one, we see we generated where it came from. So we generated where NH4 plus came from. And most importantly is we see that we produce H3O+. So without even doing a calculation or picking up your calculator, as soon as you write this reaction correctly, you should be able to make the prediction that we would expect this salt to be acidic because it's producing H3O+. And also important when you do the calculation, again here, a Ka value, because it is going to be an acidic solution and you did produce H3O+. So just like the previous one, you would most likely be given in a problem like this the Kb value for NH3. You would need to use that Kw to convert it to Ka. Your question is, why did we cross out Cl minus? Again, because Cl minus in all likelihood came from hydrochloric acid, and hydrochloric acid is a strong acid, which means the Cl minus, which is its conjugate base, should be relatively weak. And what that means is it will not continue to react with water. So it's considered basically a neutral salt. So anything that sort of comes from a strong acid or a strong base is considered neutral, which means it will have no effect on the pH. So that's why we ignore it. Other questions? Okay. Now, there's also another way that you can get an acidic salt, which is a little bit different than sort of your traditional here. And what's underneath there is what I wrote, basically. And we could get an acidic salt from, come back. We could get an acidic salt from the reaction of really a metal, a small metal that has a positive charge that's surrounded by something like water or ligand. And essentially what's happening in this situation here, and I'm going to draw it really badly, but I apologize in advance. We'll go with our aluminum. And basically attached to your aluminum is you have 5 waters attached. So I'll just draw all these waters like so. Oops. 1, 2, 3, 4, and 5. And the 6th water, I'm going to actually draw out like it would be. I'm going to draw it even bigger so I have room to draw it. It's not really that big, but your sort of 6th water, if you will be attached here. The aluminum, which is positive 3 charge, would be attached to the negative side of the water. And what happens in this situation is you got these 6 waters attached to this positively charged metal. And what that does is, again, as we talked about, this is a polar bond. So the electrons are sort of moving in. And you got this really highly positive charge, which is going to make those electrons move in even more. So just like we were talking about with acid strength, that's essentially going to weaken that bond pretty good. And what's going to happen is another water not attached to the metal is just going to come around, and it basically is going to grab that H off. And when it grabs that H off, that is where we produce H3O+. As you can see, it's the same as H+ is produced. And you may look at this thing and go, that looks a little crazy. You'll be able to name that at the end of the semester. But if you just kind of keep track of the parts, this guy has an aluminum, which is our aluminum here. There are 5 intact waters, which is 1, 2, 3, 4, and 5. And what's left is OH, which is what you get when this H pops off, right? You're left with just the OH there, and that's sort of all the parts of it. But in terms of what we're talking about here, the important part is it will produce H3O+. So again, without doing any type of calculation, we won't do any calculations that involve metals like this, but you would know that it is acidic. So there's 2 sort of basic ways you could kind of get an acidic salt. One, a more traditional route like the top way. The second one, small metals that have high positive charge can kind of do this when it's in solution. Any questions on that? All right, so let's take a look at some examples and how to do some of these calculations that involve salts. So first off, I will give you a chance here to try it yourself. What is the pH of 0.45 molar potassium chloride solution? And you even got some choices there. Hopefully one of those will be right. So why don't you take a minute or so and try to think about what you think the answer is, and then we'll talk about it. Okay, so let's talk about it. Just so you know, there's no calculation actually needed on this particular one. So when we look at this salt, which is KCl, This is, again, when you kind of want to think backwards about where it perhaps came from, right? And this most likely came from KOH, which is potassium hydroxide, and HCl, hydrochloric acid. So if we want to dissect this salt, this is K plus and Cl minus. K plus, which is group 1, as we talked about earlier. Group 1 is a neutral salt, right? So we don't have to worry about that. It's neutral. And again, it most likely came from this strong base. Cl minus, also a neutral salt because it came from HCl, which means they are all neutral there and no calculation actually needed. The pH of this guy should be 7 in that case. Again, basically, although I crossed them out, they're both technically neutral salts and should have a pH of 7. Any questions on that one? So let us actually take a look at one where you do need to do a calculation. And let's do this one together here so you can again see how it works. So when you have to do sort of a calculation involving a salt, what you need to do is probably find your calculator. There it is. There we go. But more importantly, what you need to do again is sort of think about the salt and think about the parts of the salt and if anything will go through hydrolysis. So the salt we are dealing with here is sodium fluoride. And when it breaks apart, it's going to break apart into Na plus and F minus. So again, it's sometimes helpful to try to visualize where these things come from. And since we're talking about acid and bases, you can make, again, a pretty good estimate as to where it came from. Sodium probably came from sodium hydroxide. F minus is the conjugate base to hydrofluoric acid. So we already know that the sodium part here is group 1 and will not affect the pH. It's neutral. So we don't have to worry about the sodium part, again, also because it comes from our sodium hydroxide. But now the F minus really did come from our HF, and we know hopefully that our HF is a weak acid. And you may say to yourself, how do I know that's a weak acid? Because if you keep reading the problem, I see a Ka value for HF, and that's a pretty big hint that the HF is a weak acid, right? So Ka values only for weak acids, just like Kb values would only be for weak bases. So again, there's a lot of information in these problems, and you want to make sure that you actually look at it because it can give you a good amount of information to help you sort of solve these problems. And very often people overlook the actual information in the problem to help them. So, you know, a lot of times numbers and stuff are there for a reason. It can sort of lead you down the right path. So what we do know is because F minus came from a weak acid, this is going to be relatively strong, and this will go through hydrolysis. The other thing that we know is because it came from a weak acid, this guy, technically speaking, is like the conjugate base. And that's really important for the reaction we're going to write, which is F minus. When you go through hydrolysis, it's got to be water involved, so it's just water. And because we know it's going to act as a base, it's going to accept the H plus over there. And that's going to produce HF. And we will then produce, as we produce that HF, we will get OH minus. So a couple of things about the equation here. First off, just like we saw earlier, we produce where it came from. And sometimes people have a hard time with the equations. So the good news is that also is usually found right there in the problem. So you could actually find it to help you out. The second thing is, before we do any calculation here, we should already know that our result of pH should be basic. And it should be basic because we are producing hydroxide. So there's a lot of information that you could get from just writing the correct equation. We already know that once we're all said and done, we should end up with a basic pH. Any questions on that so far? So to solve these problems, we're going to use our good friend, the ice table, because, you know, what else would we use in this class? We're going to use ice table here. So we have 0.3. Obviously, the 0.3 molar, it's a one-to-one relationship between the sodium ion and the fluoride ion, which means the fluoride ion is 0.3 molar as well. We're going to do 0 and 0 on these guys. We're going to do a minus x, plus x, plus x. And we're going to go 0.3 minus x, x, and x. Any questions on the ice table? You also see I did nothing here because this again is water, which as we know does not participate in the equilibrium. So good not to put letters or numbers and things you shouldn't be using anyway, so you don't mess up. This is going to go into our K expression here. So K would equal our products, which is HF, OH minus, divided by F minus. And by the way, this should be a KB. Again, that's why this part here is important. It should be a KB value. So as I said a couple of times at this point, just like normal, they give you the sort of wrong K value, if you will. We have the Ka value, but we actually need the Kb value here. So we are going to want to use our relationship that we saw earlier here at the beginning to get that. And that again is Kw equals Ka times Kb, which means Kb would equal Kw divided by Ka, which is 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. And that's going to give us a Kb value of we'll call it 1.4 times 10 to the minus 11. So that is the number that we want to make sure that we use here. Again, because we produce hydroxide, we should be using a Kb value. Even though you're tempted to use that Ka value that they give you, you need to make sure you're using Kb in this case. Just like normal, we're going to slap our things in here. So that's x squared 0.3 minus x equals, again, our Kb value. Hang on a sec. I got some stuff in my way. Come here. Go that way with it, maybe. There we go. And I got too much stuff in my way. Hang on. There we go. And we're just going to get, I'm just going to drop my camera feed so I can actually see my screen. There we go. All right. So to the minus 11 here. And we can assume that x is equal to 0 in this case. Again, the K value is small, so we're going to take 0.3 times it by 1.4 to the minus 11, making sure we use our exponent button. We're going to take the square root of it. And looks like you get, if you do all that, you got, what did you get there? You get x squared equals 4.2 times 10 to the minus 12 gives you an x is equal to a lot of zeros there. We'll go with 2.0 times 10 to the minus 6. We do want to make sure that we check it. So we'll take our 2.0 to the minus 6. We'll divide it by 0.3 times it by 100. And we're good. We're nowhere near even 1%. So the check is good here. That means that when we finally go to our table, we see that x is equal to our OH minus, which means our OH minus concentration is 2.0 times 10 to the minus 6. That gets us our POH. And our POH then would be, looks like 5.70. And that means that our pH would be 14 minus 5.70. And we got something like 8.30 as the pH. And 8.30 is definitely basic, and it does make sense with what we expect it to be, which we expect it to be basic as well. Any questions on that there? I'm thinking about it. I'll let you know. It'll be on the test shortly. Any questions on it? All right, let's give you a chance to try it. So give it a chance, give it a try, see what you come up with. Okay, let's take a look at this and see how we're doing. So again, here we have a salt, which is sodium cyanide. So again, we want to look at the sodium cyanide and think about how it breaks apart into sodium ion and the cyanide on it. As we talked about a number of times up to this point, we know again that the sodium is going to be neutral because it's group 1, so we don't have to worry about it. Again, we want to think about where this came from, and as I mentioned before, there's oftentimes very big hints sitting right there in the problem. We see HCN, that looks like where it might have came from, and we have a Ka value, which tells us it's a weak acid, which means technically speaking, this would be our conjugate base, and this would go through hydrolysis with water because of that. So that's where we want to start. We want to start with our hydrolysis reaction, which is Cn minus plus H2O. Again here, since it's going to act as a base and it's going to accept the H plus. By the way, logic also tells us it doesn't have an H to give, so it's got to accept it. And we will get our HCN and our OH minus in this case. So again, without even doing a calculation, we already know that this guy should be basic, again, because we are producing OH minus here. So we definitely know it should be basic in this case. Any questions on the reaction or equation here? We also again see where people struggle, what it makes. That is also usually given to you right there in the problem as well. So you can see you get that as well. So we're going to do an ice table here. So initially we got 0.75. It's a reversible reaction because it's still a technically weak base, even though it's relatively strong. So remember, when we talk about sort of relatively strong, the Cn minus, for example, the Cn minus is relatively strong in the sense of weak bases. It's much weaker than, say, a strong base or something like that. And that's why it's reversible, really. So we will get our 0 and 0, and also why we can set up an equilibrium, right, and use our K value and stuff like that. So that would also imply, obviously, it's a reversible reaction. The change would be minus X, plus X, and plus X, and we would end up with 0.75 minus X, X, and X. Going to go into our K value here, which is our products. Divided by our reactants. And again, in addition to knowing that it's going to be basic here, this should also be a pretty big red flag. I need a KB value, which obviously, as you can see here, I do not have. So this again should be a KB value. So we'll use our KW expression there to help us. So our KB would be 1 times 10 to the minus 14, which is KW, divided by the Ka value. And that will get us 1.6 times 10 to the minus 5. And again, we want to make sure we would use that value here. So putting in our values, x squared divided by our reactant side there. Try to get rid of that extra little line. There we go. So we have, again, x squared divided by 0.75 minus x equals, again, our KB value. We're going to assume x is equal to 0. And again, that's going to give us x squared 0.75 equals 1.6 times 10 to the minus 5. We're going to multiply the bottom, the 0.75, to the other side. We're also going to take the square root of it. And that will get us a X value of, we'll call it 3.5 to the minus 3. We do want to check it, so we would take that, divide it by 0.75, and times 100, and you got something like 0.46%. So the check here is good. In a lot of cases, you'll be okay, usually on the assumption here, but still should check it. And as we can see again from our table, X is equal to the OH minus concentration, which means our OH minus concentration equals 3.5 to the minus 3. That's going to give us our POH, which is minus the log of 3.5 times 10 to minus 3. That will give us a POH of 2.46. And again, remember that that is not the pH, but that's the POH. So to get the pH, we're going to take 14 minus 2.46. And I was like 1154, which I would say is basic and would make sense in this case. Any question on any of those sort of steps there? So when we deal with salts, it does require, as you see in these couple examples here, it does require an ice table. The key sticking points for a lot of people are being able to correctly write these equations. Again, being able to write these equations where you either produce OH minus or H3O plus. And obviously, the very biggest thing that people mess up on is they use the Ka value when they choose the Kb value, or vice versa. They use the Kb value when they choose the Ka value. So a acidic salt works the same way. The only difference is on the product side, you would produce H3O plus instead of OH minus. And the other difference would be once you solve for X, you could go right into the pH equation. Any questions on hydrolysis problems or salts? Okay. Here's a much prettier picture of what I drew with the aluminum, but again, that would be the aluminum in the middle. We have our waters, and again, you can see another water will come and take the H off of it, and that will produce our H3O plus, which will give us an acidic salt. And again, sometimes a small metal with a positive charge has the ability to do that. Now, up until this point, sort of the calculations that we have done involve really only one part of the salt going through hydrolysis. So for example, either CN minus or the NH4 plus part, but not both parts. And it is potentially possible to have a salt that was produced that both parts can go through hydrolysis reaction. So for example, if you had, say, this salt, ammonium fluoride, the ammonium would come from NH3, which means this part of it, which is NH4 plus, should go through hydrolysis. The F here would probably come from HF, which means this part of it, which is F minus, would also have the ability to go through hydrolysis. So if you try to do the calculation for both of them together, it's very complicated. So typically what we do in a case, if we should ever come across a salt where both parts of it, so like in this case, both parts of it could go through hydrolysis, we actually compare the Ka value to the Kb value. So if you compare the Kb value for the anion, the negative guy, and it's greater than the Ka value for the positive guy, you would assume that that salt would be basic, and you would pretty much just do the calculation for the Kb part, the basic part of it. If you looked at the Kb for the anion or the negative part and is less than the Ka value for the cation or positive part, you could assume that the solution would be acidic, and you can do a calculation based just on the Ka value in that case. if you had a Ka value and a Kb value that was about the same number, then it would probably be neutral. Again, you would have to analyze the salt and see and think about where they came from, like I just did here on the screen. Something like NH4F, the NH4 part is NH4 plus, which most likely came from ammonia, which is a weak base, which means it should go through hydrolysis. The F minus most likely came from, in this example, HF, which is a weak acid, which means it also should go through hydrolysis. So it really is important, the salt that you're looking at, and sort of analyzing like you do sort of with the ones we've already did as well. So it would be basically that both parts of the salt basically came from something that's weak. So usually in the examples that we've done up to this point in terms of calculations, the salt part that goes through hydrolysis is the part that comes from something that's weak, and the other part comes from something that's strong. So in this case, both parts would come from a weak acid and a weak base, right? Which would be like if you mix these two guys together, right? Weak acid, weak base gets you this salt here, yeah? Other questions on that? So I wouldn't anticipate in our class that you'd have to worry about necessarily doing a calculation like this, but it's potentially possible. But again, that's sort of how you approach it to make it sort of manageable. You either would do sort of the acid calculation if the Ka was larger, or you would do the base calculation if the Kb value was larger. Any questions on that there? And that's what this little table here shows. And that's another table from your book. You have a similar one there that kind of shows what we talked about with the different types of salts. And again, here you can see in both of these examples here, both parts of that salts, or both of those salts, or both parts of each of those salts will go through hydrolysis. We have ammonium acetate. Ammonium, again, comes from NH3, which means it will go through hydrolysis. And acetate comes from acetic acid, which means it could go through hydrolysis. And again, ammonium cyanide, ammonium, again, from the ammonia, which means it goes through hydrolysis, and HCN, which is hydrocyanic acid, also is a weak acid, would go through hydrolysis. So I don't anticipate you having to do a calculation like that. But again, in case you did, you just want to figure out which one's larger, Ka or Kb, and then you could do the calculation based on either the Ka calculation or the Kb calculation. So let's talk a little bit about oxides. So oxides are elements that obviously contain oxygen. And depending on where they are on the periodic table, they will sometimes, when they react with water, produce either a base or an acid. So that's why they're sometimes referred to as basic oxides or acidic oxides. So they're in group 1 over here. Group 1 and group 2, as we talked about a number of times, that's where a lot of strong bases come from. So you take something like sodium oxide, magnesium oxide, potassium oxide, and sort of react it with water. You'll generate like sodium hydroxide, potassium hydroxide, and so forth. So that's where a lot of strong bases come from. So those are referred to as basic oxides, as opposed to on the other side of the periodic table where we got kind of nonmetals involved, nonmetals with oxygen. When they react with water, will typically produce acids. So like we see on the bottom here, CO2 plus some water will make carbonic acid. N2O5 plus some water will make some nitric acid. So a lot of the acidic oxides are found to the right and upper part of the periodic table, right around that staircase and into the nonmetal region. And then we do have some of these, I don't know what color we call that, but these colors there, that are amphoteric. So just like we talked about before, amphoteric means that it could act either as an acid or a base. So again, those guys could kind of go either way in it. Any questions on that or where those guys are located? Now, we've talked about a couple different definitions of an acid and base in this chapter. Arrhenous acid and base is basically something that will produce H plus in solution, while a base will produce hydroxide. We had our Bronsted-Lowry definition of acid and base, which is a proton donor and a proton acceptor. And our good friend Lewis couldn't be left out. When we think about Lewis, we think about Lewis structures, and we also think about Lewis structures electrons. So Lewis came up with sort of a definition of an acid and base that oddly dealt with electrons. And a Lewis acid is a substance that will accept a pair of electrons. And a Lewis base is one that will donate a pair of electrons. So opposite of Bronsted-Lowry in the sense of donating and accepting for your acid and base, but also dealing with electrons here. So for example, what we see here in these few examples here, we have OH minus, which is going to donate a pair of electrons over to the H plus, which is going to accept a pair of electrons, and that makes it the acid, and this makes it the base. When we have something that has the ability to be a Lewis base and donate a pair of electrons, you want to think about things that have lone pairs, kind of polar, and things with negative charges are very good at that, because things with negative charges implies that it gained electrons along the way, which means it probably has some electrons it could donate, while things with positive charges are usually electron deficient, which means they are probably good Lewis acids. So H plus means it's kind of electron deficient. It will be willing to accept the electrons. And here we form water. NH3 is a polar molecule with those non-bonding electrons. So polarity here being a polar molecule helps those electrons be transferred over. And our NH3 is our base and our H plus is our acid. And that's sort of our regular definition, right, of acid and base with Bronsted-Lowry. You can still use the Bronsted-Lowry definition to help you figure it out as well. Now, just because you have electrons doesn't necessarily mean it can be transferred. It does need to be usually some type of polar situation, some type of separation of charge that helps it out to donate it. We will see Lewis bases again later on when we talk about coordination chemistry and complex ions. But again here, Lewis acid, something that can accept a pair of electrons. Lewis base, something that can donate a pair of electrons. And the nice thing about sort of the Lewis acid base definition is you can apply it to something that does not involve a proton being transferred or accepted. So here we have BF3, which is an exception to the octet rule. It is less than 8 electrons, definitely electron deficient, which means it will accept the electrons and become the acid. NH3, as we were just talking about, being our polar molecule, will donate those electrons and become our base. And again, sort of the broad approach for Lewis acids and bases is you can apply it to maybe a more non-traditional sense of acid and bases. We oftentimes think about acid and bases in terms of H plus being donated or H plus being lost. Any questions on that there? Okay, so that will wrap up lecture portion of the festivities here for today. We have lab coming up in about 10 minutes or so. And here's the deal. We are going to continue to lecture in lab today. We're not going to actually do a lab. So we're going to continue to lecture. We have just one more topic here in this chapter to talk about. And we're also going to get into the next chapter, which the notes are found up online as well, just to kind of put us back on pace. And after we're done lecturing, I will obviously let you know about the exam and exactly what material will be on the exam after we're done lecturing and stuff like that. So we're going to continue to lecture, and just to ease any anxiety, what we're going to continue to lecture on will not be on the exam. So we're just going to continue to lecture to sort of stay on pace. Yes, I'll try to get there up. I'll try to get it up there obviously before tomorrow. Again, it does take us a little bit of time, but I'll try to get it up there as soon as I can. Okay. Yeah, let's just go through the lab. That way, that will actually allow me probably to get this up there a little bit quicker. So go through the lab link like normal, And that way this recording will end and it'll kind of process and everything like that, so that I can kind of get it up there for you and everything, okay? So go through the lab link. In terms of today's lab, I think what we're going to end up doing is move it to Monday with the other buffer lab and maybe do them both together or parts of both of them. So we're not going to skip the lab that was scheduled for today. We'll probably do some part of it along with the buffer lab that's scheduled for Monday. And since we haven't got into buffers, that's the next sort of topic. In the next chapter, I want to continue lecturing to get into that material to keep us on pace and kind of get us back on pace and all that good stuff, okay? So again, pretty much what we're going to lecture on is not going to be on the exam. I will let you know what from what we just lectured on will be on the exam after we're done lecturing there in lab and stuff like that. Any questions on any of that? If you did not type here in the chat box, make sure you do that. Again, make sure you come through the lab, and we'll start lab at about, since we're a little long, maybe like 3:10 we'll start lab, okay? All right.